Okay, so good morning, everyone. First of all, I would like to thank Antonio for giving me this chance to share our work with you. And something about me. My name is Zheng Lui from NTU. Actually, I'm very fresh here. I've been here only for 3 months. So I moved from Rice University and across the ocean and to NTU here. So probably would like to see what exactly my lab looks like. It is just on the white paper. So my lab actually belongs to a new building that is under construction. So hopefully I can make it around by the early of next year. Okay, so outline. For physics, for 2D materials, they would like to stacking them together like playing a Lego game. But for our material guy, maybe you would like a good chef, we're cooking something, cooking different materials. So for this talk, I will give a very brief introduction for 2D materials, and then the dish for the BCN system. And the second is another dish for the transition method Dichalcogenides system, including the synthesis of materials, doping and oiling, and the hybridize of these structures, and then very brief summaries of this work. So since the discovery of graphene, I think almost a decade has passed. Now I call this time the post-graphene time. In this time, we are in the transition from the graphene-only material to a variety of layered materials like silicon, nitride, TMD materials, and oxide. And also, to the synthesis of fabrication, we are shifted from the optimized synthesis for graphene to the modification and artificial structures of different 2D layers. And also, for the application, we shifted from the graphene-only application to the full integrated multifunction application consisting of various of 2D layers. So my talk will focus on the nitride BNC system and the TMD system. So for the boron nitride, first of all, boron nitride is a very flat material, as you already know. So the average roughness of boron nitride is only 1/5 of that of silicon oxide. So if we can put boron nitride on graphene on boron nitride, the mobility it can be significantly increased to close to the intrinsic limit. And also boron nitride is a very stable material that can resist the high temperature and also chemicals. So for boron nitride, if you oxidize at 1,000 degrees, it can be stable, it can still survive. But as a comparison for graphene will degrade at a temperature of 500 degrees. So the second point, boron nitride is wide band gap material. The band gap is 6 eV, so which means boron nitride is a very good candidate for the far-violet, far-ultraviolet source. For the next generation semiconductor industry, the lithography machine is very important, and the light source, high-quality light source, is an essential part for the lithography machine. And the boron nitride maybe provide an opportunity to make some high-quality light source. Okay, now let's move to the TMD. TMD actually big families consisting of more than 20 members, and they're probably the biggest family for the layer materials. And we actually can find a lot of layer material in these families with 2T or 1H atomic structures, and many of them very stable in air or in water. Okay, molybdenum sulfide is a very typical member in this big family, and it has been commercially used for lubricant, but now the reason we like it is because we have a highly electric conductive graphene, and we have insulating boron nitride. So molybdenum sulfide is the last piece we're looking for as a narrow bandgap materials. And because of this narrow bandgap, the on-off ratio of molybdenum sulfide can be as high as 10^8. And also, if we can make the molybdenum sulfide from the bulk to thin layer, we can see the transition of direct bandgap to indirect bandgap to direct bandgap, which will result to the valetonic properties of these materials. And also Noah mentioned the catalyst and linear optic properties. I think all of these properties have been discussed in previous 2 days. Okay. So, and then next, if we can get some materials, different layer materials, we will think, can we combine them together? Can we integrate them together to get some artificial layers to make them whatever we want in terms of the functionality? So now we have boron nitride. Boron nitride actually can be a very good substrate for graphene and also for possibly other 2D layers. And also we have a different band gap from 0 to 6. Is it possible to make artificial layers with the tunable band gap from 0 to 6 eV? And also, is it possible to make artificial layers which can get reasonable good mobility as graphene and also good on-off ratio as moly disulfide? So we have a lot of dreams. So reality, we have 2 ways to go. The first, we can stack them together to get super lattice structures. And we can control the ordering and the species in each layer to get whatever we want. And the second way, we can stick them together like this part graphene, that part boron nitride, that part is moly disulfide. And from here, we can get the temperature. From there, we can get the strain. And also, we can do computation in this layer. So for a single sheet, we can get quite a lot of information than the graphene. OK. So let's move to the first story, the B-thin system. B-thin system actually been studied by the theorists a lot of years, and it's kind of complicated because the C can be graphene, the B can make boron nitride, and the boron carbon and carbon nitride structures, and also have some ternary system with different physical properties. So I won't go into details because it's time sensitive. So for this B-thin system, first of all, I will introduce how we prepare the boron nitride atomic layers, and then how we make some carbon nitride atomic layers. And then the third part will be the ternary BCN atomic layers with different approaches. The last part, I think, will be how we convert graphene to boron nitride. Okay. For the synthesis of a boron nitride, we use ammonium boron as the precursor and the copper and nickel foil as the substrate. So we've been spent a few years to working to improving the quality and to control the thickness of this material from the bulk one to fill layer to down to double layers boron nitride. And this is the STEM imaging showing the double layers of boron nitride, and also you can see the different ages layers from more than 20 layers, 4 layers, 3 and 2 layers boron nitride. And if we can pair up the top layer of boron nitride, actually we can get a defect-free monolayer boron nitride with this bright dot nitrogen atoms and this dark side boron atoms. And just like I mentioned, boron nitride is material resistant to very harsh conditions like high temperature oxidation. So a very natural idea is, can we coat boron nitride on different surfaces and as high performance anti-oxidation layers? So what we have done is we coat the 5 nanometer boron nitride on different metal surfaces like nickel, stainless steel, copper. And then we oxidize them at a high temperature, such as for the nickel. We oxidize at 1100 degrees. And without the coating of boron nitride, what you can see is the surface of nickel has been destroyed, and a lot of nickel oxide grains. Okay, but surprisingly, with the coating of boron nitride, you can still see the texture, the grains of the nickel, and the whole surface has been preserved, protected very well. And the same case for the stainless steel and the copper foils. And next, what will happen if we transfer this material to graphene? So here, we have a boron nitride part of the graphene. This part is graphene without boron nitride. This part is the boron nitride coated graphene. And then we burn it at a different temperature from 200 degrees, 600 degrees, and 1,000 degrees. So from what you can see is here. Without coating boron nitride, graphene have been burned out, for sure. And there's no Raman signal from here. But with the coating boron nitride, we can still find the signal from graphene. So this work means we can use boron nitride, the ultra-thin boron nitride, for very good coatings for both some metallic surface, also for graphene for high temperature workable devices. Okay, here's the story is the part of boron nitride and carbon nitride. Carbon nitride is kind of strange because not like graphene and boron nitride, the atomic structures for carbon nitride is not that stable or maybe not that fixed. So it's really hard to get a TM imaging of what the carbon nitride looks like. Here we use the commercial carbon nitride bulk and use the liquid deflation method. We can get some atomic layers carbon nitride. And we can get some TM images showing the atomic structures of the carbon nitride, and also showing the diffraction patterns here. And also we can dope the iron to this lattice. This iron can be the individual iron atoms or a cluster of a few iron atoms. And this material actually is a very good catalyst for the water splitting. That is hydrogen evolution. Okay, so we move to the B-thin system, the ternary system, consisting of graphene and boron nitride. So what will happen if graphene meets boron nitride? What the B-thin ternary system looks like, I just mentioned, we have two ways to make them as the artificial layers. We can stack them, or we can stitch them to the planar structures. And this is an old story we did 3 years ago. We introduced the boron sources, boron nitride sources, and the carbon sources to the furnace. And then we can get the B-thin atomic field like this. It's atomic layers from 2 layers to a few layers. And then from the TM imaging, you can see it consists of the boron nitride and the graphene domains. The size of domains are a few nanometers. And we can also tune the concentration of boron nitride from 0 to 70%, that we can tune the transportation behavior for these atomic layers. And the problem is that for this material, this kind of boron nitride and graphene domains, they are random distributed. So we are thinking, can we control the domains of graphene and boron nitride? So the way we were doing is, first of all, we grow the boron nitride, and then we etch part of the boron nitride, and then we regrow the graphene in the etched areas, which we can get some planar graphene boron nitride hybrid structures. And this film can be transferred to some rigid substrate like silica, and also some flexible substrate like PDMS. And because of this method, we employ the photolithography process, so we are able to make some complicated patterns like this is all the log of rice. And also we can make some circles, some squares, triangles. And we examine the interface of these materials under microscopy. We can see this is a very sharp interface, but because of the contamination problem, we can see the atomic resolution image show how they bonding with each other. And okay, if we can make a structure like a strip of graphene stripe for boron nitride at relative strips, so we can get the image like this. There's a sample, and if we put a contrast in this way and the flow along the graphene channel, we can get the mobilities comparable to the Princeton graphene. And okay, if the current flows perpendicular to the graphene and boron nitride strips, then we can get nothing. So structurally, we get actually anisotropic FET devices. And we also demonstrate that if we made some graphene lines and fed by the boron nitride, we can get graphene-boron nitride planar radio frequency resonators, and the response frequency is around 2 GHz. So this work tells us that we are able to control, we're able to shape engineering the graphene-boron nitride planar structures. So we can design whatever we want, this, which areas is boron nitride, which areas graphene, to meet our needs. And if we can incorporate the TMD material in this system, I think the system might be much more interesting and fantastic. Okay, so this is the final story in the BCN system, because as you already know, the lattice constant for graphene-boron nitride is very, very small. This mismatch only 1.8%. So is it possible to convert graphene to boron nitride using substitution way? So here we start with the CVD graphene, and then we use the boron acid as a source of boron, and use the nitrogen ammonia as nitrogen source. At high temperature, the carbon atoms has been substituted by the nitrogen, boron, and finally, we can get a fully converted boron nitride. And this is a partially converted boron nitride. What you can find is some areas the boron nitride, and some areas the graphene. This is the Raman signatures. And we also examine the quality of these materials. This is the CVD graphene before conversion, and this is the boron nitride after conversion. So the quality is reasonably good. And for the partially converted BCN sample, in the microscopic, we can see some nanodomains, boron nitride nanodomains embedded into the graphene lattice.
About what temperature?
1,000 degrees. And okay, furthermore, if we can protect part of the graphene areas, and we convert the rest areas without cover, without coatings, we can convert these areas, exposed areas, to boron nitride, and after we add this protector, we can get a graphene boron nitride hybrid structure again. This is also the shape engineering. But we can step to the next step, which we can protect some areas and convert to BCN, and convert some other areas to HBN. So which means in a single layer, we can get a graphene, boron nitride, and HBCN, the three different composition in a single sheet. And what more interesting is that if the concentration of boron nitride is 40%, then we can get the maximum on-off ratio up to 1K, and also the mobility is also up to around 1 to 2K. So comparing with molybdenum sulfide, okay, its mobility pretty high, and then comparing with the graphene, we get a much higher on-off ratio. So this material maybe have some possibility for electronic devices. So I won't say it will beat the silicon, because we have a lot of work to improve it. And also we compare it with different the film FET materials like organic, amorphous silicon, and carbon nanotube networks. So these materials, and this is what the material we can make. Okay. So I just discussed the planar structures. How can we shape engineering the planar boron nitride and graphene? And I just mentioned another way is stacking them together. So we developed two ways to stack them together. The first way, we can grow with graphene first, and then we deposit a boron nitride on graphene. So like showing here, this graphene only, this boron nitride on graphene. So we use different technologies to determine the structure of this material. The graphene actually is monolayer graphene, and the boron nitride is on top of graphene, and the thickness few layers boron nitride. And the second way is we can use the liquid exfoliation method to make some boronitride flakes, atomic flakes, and graphene atomic flakes. Then we simply meet them together. Because of the self-assembling process, we can get a lot of graphene boronitride stacks from the valve solid. So this method, we can get controllable thickness, and for this method, we can make a large amount of materials. Okay, now we move to the second story. The TMD families consisting of molybdenum sulfide and selenium, and maybe a tungsten. So I have 3 parts. The first part is how we synthesize these materials. The second part is how we doping and alloying these materials, and also the hybrid structures of the different layer materials. Okay, because molybdenum sulfide is really interesting these 2 years, most people are using the mechanic, use the tape to make monolayer, molybdenum sulfide field layer. It's really time consuming, and probably you can get only a few devices in 1 week. So we are thinking, can we use safety method to make larger areas and reasonable quality samples? So at the very beginning, we deposit a very thin layer moly on the silicon oxide, and then we introduce the sulfur to start rising these materials at 800 degrees. And what we can get is 1 centimeter square molybdenum sulfide. And using the Raman mapping, using the bright field image to the false color dark field image, we know this film actually is consistent of a lot of nanoscale flakes. The size of these flakes is tens of nanometers, and thickness from 1 to 3 layers. But this is not enough, because if we want to use this material to make FEV devices, the electron will hop from 1 flake to another flake. So the performance will be pretty low. And also, if this thin layer of moly haven't been reacted with the sulfur completely, the remaining moly layer will destroy this device. So to improve the quality of these materials, we replace the moly films with the moly oxide. Actually, oxide is really important for the synthesis of TMD materials, but I don't think anyone can get a very clear idea how it works. But it works for many of the TMD materials, tungsten disulfide, molybdenum sulfide. Maybe this is another story. Okay, from this method, we can get the single layer, the single crystal, single layer molybdenum sulfide. And from the FM height topography, the thickness is 0.7 nanometers. And we can also get large areas, polycrystalline monolayers, so a couple of hundreds nanometers, 100 microns. And also we examine this material under microscopy. So a lot of areas that defect-free. And we can get quite a lot of different shapes, like triangle, like symmetry, like hexagons or stars. And we make some devices, and the test is the mobility and off ratio. The mobility is 0.1 to 20, and the mobility 10 power 8. So these values are comparable to the mechanical exfoliated molybdenum sulfide. Okay, since we can make such a high quality and large area devices, we would like to see what exactly it looks like in terms of thermal structures. Okay, so we got some beautiful defects. So we look at the point of defect. Because the molybdenum sulfide consists of the sulfur, moly, sulfur, 3 layers. Okay, so the defect varies a lot than graphene. So for the point of defect, we can get quite a lot of, like the 1 sulfur vacancy, 2 sulfur vacancy, and 2 sulfur substituted by a moly. And even more cases, more than 6 type of defect. And so one thing I would like to mention here is this defect actually is potentially active site for catalyst. So if we can control the density of this defect, probably we can get a high performance catalyst material using the molybdenum sulfide. Okay, so next we move to the line defect. So in this materials line defect, we've been observed 2 kinds of line defect. The first one, if 2 molybdenum sulfide domains growing bigger and meet each other, they will form ground boundaries. like graphene. Actually, the ground boundary, because of the 3-layer molecular sulfide, we have a lot of variations. Here we show 4 different ring structures along these ground boundaries, and the corresponding the SDM imaging showing the distribution of ET atoms and the shape of this ring structure. And another case is if 2 molecular sulfide domains growing bigger, meet each other, instead of forming a ground boundary, they keep growing on top of each other. So which we can get this overlap structure. The right part is a monolayer, the left part is a monolayer, and this is the overlap of the 2 monolayer molybdenum sulfide. Okay. There's one thing very interesting is that if the rotation angle between different domains, if the rotation angle is 6 degrees, like I'm showing here, 60 degrees ground boundaries, this line actually from the calculation is metallic. So this is the only case, the metallic ground boundaries in molybdenum sulfide. We also look at the edges of this molybdenum sulfide, but unfortunately, because of this edge is not that stable under the microscopy, so we get just a few images. But anyway, from this image, you can see the configuration, the reconstruction of the sulfur and the moly atoms along the edges. So it's not that stable. Okay, using microscopy, you can easily identify the ground boundaries, but that is kind of expensive and time-consuming. Can we figure out a very easy way to identify the ground boundaries, like using PL mapping? Okay, this is monolayer molybdenum sulfide star, and from the PL intensity mapping and the PL peak location mapping, we're able to tell how many ground boundaries we have, 6 here, and where are they. So this way give us a very quick way and a no-contact way to identify ground boundaries, and maybe very good for the the device guys. They can know where are they can put contacts on them. All right. The band gap, the strain-induced band gap renewing is also a very hot topic in these 2 years using the TMD materials. So there I have 2 things to share with you. The first thing is, for CVD molybdenum sulfide, there might be some pre-existing tensile strain in this sample. Okay, this is the S-ground molybdenum sulfide on silicon oxide, and then we transfer them to another silicon oxide. And what we can find is that there from 0 to 1% tensile strain in the S-ground materials. And the PL spectrum is also different from shift from the left to the right. And also, another problem is how much strain can be transferred from the substrate to the molybdenum sulfide. So here we put the molybdenum sulfide on the PDMS, and we're applying a force along this line. And actually, the molybdenum sulfide has been deformed. And then at the same time, we collect the PL mapping for different tensile strain from 0 to 5%. And we do see the shift of the PL peak. But definitely this is not corresponds to the 5% strain. So only part of strain can be transferred from the substrate to the molybdenum sulfide. So what's the problems? So by the infinite element calculation, what we can see is the Young's modulus of a subject plays very important roles. So if you can make the Young's modulus more than 1 gigparts, most of the strain can be transferred to the molybdenum sulfide in the substrate. So Young's modulus is really important for this kind of strain experiment. And okay. As we previously discussed, the B-thin system is a ternary system, but unfortunately, for most of the case, they won't become the homogeneous ternary system. Instead, they will get some domains, boronitride domains and graphene domains, because of the phase separation. But the TMD families give us another playground for the ternary system, and possibly we can get this true homogeneous ternary system. So here we have a moly disulfide here. Is it possible to substitute, to dope the selenium into this lattice, like showing here? And here's some challenge. How can we grow these materials? And how can we qualify the atomic structures of this ternary system? And also, how can we band gap engineering these materials? So we start from the mixed powder of selenium and sulfur, and under the similar conditions with the moly disulfide, we can get some flake here. Okay, this is a single crystal monolayer triangle, selenium doped moly disulfide. From the FM, the thickness from 0.7 to 0.8 nanometers, corresponding to monolayer. And this is our synthesis protocol. We can also grow some polycrystalline and also the film-like films for the selenium moly disulfide. So from the XPS spectrum, from the 10% to 75%, you can see the peak from the selenium comes out, and also for the selenium 3D peak, it becomes stronger and stronger. Okay, maybe before I move to the TM part, I give a very brief introduction for how to read these images. All the TM imaging we taken is using the annual dark field STEM image. And for this kind of image, you will see we have different atoms, and they are all bright or dark. Actually, the intensity of each atom has a relationship with the atomic numbers. Briefly, a short word is, the heavier the atom you have, the intensity is much higher. So this is the moly disulfide, defect-free moly disulfide, this moly disulfide monolayers. So this bright atoms are moly, and this is sulfur. And if we can do some, do some statistic for all the intensity, we get the heterogram of this intensity, which here, this is the intensity of moly, and this is the intensity of 2 sulfur. And we have some areas that have 1 sulfur defect, so we can get a very small peak here. Okay, what will happen if we dope selenium to this system? You can get like these very bright areas. So this is double selenium, 2 selenium atoms. And some areas not that bright. This is more. This is selenium and sulfur. And the very dark side, there are 2 sulfurs. And this periodic bright side, the moly. So we can also get the heterogram of the intensity distribution of moly, selenium plus sulfur, 2 sulfur, 2 selenium. Okay, so here we have a STEM image showing like this, and by resolving the intensity mapping, we're able to translate the STEM imaging to the visualized image showing the distribution of each atoms, like the white dots are 2 selenium, and the green dot 1 selenium and 1 sulfur, and the red dots are moly atoms, and the very dark green dot are the 2 sulfurs. So from our observation in the microscopy, we have looked at a lot of places. So no separation in these materials. So selenium is homogeneously doped in this moly disulfide lattice. So this is really interesting. We never seen for the BCN system. Okay, for the bilayer case, it's maybe more complicated. So for most of bilayer, we've been seeing the TM is AB stacking. So we can still do the same thing. We can get the AB stacking, the intensity mapping of the pure moly disulfide look like this. And after doping the selenium into this system, we can get a lot of peaks here. And resolving these peaks, we can translate the bilayer selenium doped moly disulfide to each layer. And currently we can't tell which is top layer, which is the bottom layer, but we can tell the composition of each layer. And interesting is that for random site, if we calculate the density, the concentration for selenium for both layers, they're pretty close. So which means the bilayer system may be simultaneously growth. And also, we can control the concentration of selenium from 0 to 100%, which means we can go from the pure moly disulfide to the pure moly diselenide. So this is the PL spectrum from 0% to 100% selenium. And the band gap can be changed from around 0.9 to around below 0.6. So this is so-called the band gap engineering. Okay, the last two slides, I will show the possibility of making some hybrid structures using the moly disulfide and tungsten disulfide. This one, for the small triangle, is moly disulfide. And we can epitaxially grow the tungsten disulfide along surround the moly disulfide to get the planar structures moly disulfide and tungsten disulfide. And we can collect the Raman spectrum from different sites 1, 2, 3, 4. So at position 1 and 2, this is the signal from pure moly, and 3 and 4, the pure tungsten disulfide, pure moly disulfide. So these are planar structures. We can also make the stacking structures. So we have a layer of the tungsten disulfide, which is sitting on the big side of moly disulfide. Okay, again, we collect the Raman signal from 1, 2, 3, 4 position. So for 1 and 2, this is spectrum from pure moly disulfide. And for 3 and 4, this is a mixture of the Raman vibration mode of moly disulfide and tungsten disulfide. So we examine this material under microscopy. Like for the stacking, we can get a layer of moly disulfide and one more layer of tungsten disulfide overlap with each other. And for the planar structures, we have a layer of the moly disulfide here, and one more layer of moly disulfide at the top, one more layer of tungsten disulfide at the bottom. And the interface actually is kind of sharp. So we are using CVD to do something that MB can do. Okay. A very brief summary of our work. The first work is a BCN atomic system. We prepare the boron nitride. We can prepare atomic carbon nitride. Also, different approaches to the BCN system with random domains, with the shape engineering domains. And we can convert graphene to boron nitride with high quality. And the BCN has very interesting electric transportation with a very high boson ratio and mobility. And the second part will be moly, tungsten, selenium, sulfur system. These big families, we can make a high quality moly disulfide. We can dope the selenium to this system to get a homogeneous ternary 2D layers. And we can also make some vertical and planar hybrids. So I actually would like to thank for the financial support from when I was at Rice and also the Singapore NR Fellowship, and the great students, and also the excellent collaborators. So thank you very much.